So, good morning. So I'm responsible for the third workshop with the theme Energy Savings in Distributed Embedded Systems. I gave you a very rough overview yesterday. Now I will dive a little bit deeper, and at the end I will also inform you about the working tasks which should be done during the workshops. I think you know this picture from the from yesterday. I have gotten yesterday to give you information about the units of the x-axis. Because this is very important for the energy efficient orchestration, you see here the unit milli-CPU, and milli-CPU means the performance of the processor system. So if you have a processor, at example, as here with 4 cores on a Raspberry Pi, then 4000 milli-CPU means that all 4 cores are completely under full power, and 3000 means 3, 2002, and so on. This is a real important information. And I have some additional information about other parts we have analyzed in the past. So, at example, a microchip PolarFire FPGA development board, which is very interesting because it has also a processor with 4 cores, but in this case that are 4 RISC cores, 4 RISC-V cores, and RISC-V is a processor architecture which is well known that it's very energy efficient. And you see in the comparison to the slide before that in this case we have at the performance of 4000 milli-CPUs, all 4 cores are under complete full performance. Then we have only 3.6 watts, and in this at 0 milli-CPU we have a power of 3.2 watts, and you see that the difference between worst case and best case is very, very, very small. A specialty of this system on a chip solution is that there's not only a processor with 4 cores, there are also a part so-called feed programmable gate array. So there are hardware programmable resources inside, and with these resources you can realize, at example, any co-processors or, at example, an AI module, but I go a little bit deeper in one of the next slides. And my last example here, this is a very big board with a Xilinx FPGA system on a chip. There's also an ARM processor with 4 cores on the chip. The performance is comparable with the performance of a Raspberry Pi version 4, but it's a little bit another type. And on this chip, there's a big area of feed programmable gate array, and we use this part or this FPGA and this evaluation board at example for our physical layer implementation of 5G radio access networks. If you have a look on the diagram, then you see that the worst case, so we have also 4 cores, that if all cores are running at full performance, we have a power consumption of 7.89 watts. And if we have no performance or very near at no performance, we have 7.9. So you see that the difference between best case and worst case is very small. But the reason that the power consumption in all is very high, the situation is that the programmable logic devices inside this chip need many standby power. Okay, so I give you some information about our system for energy efficient orchestration. Yesterday I've said that we use the Kubernetes framework, also known in the area of data centers. But if you know you use Kubernetes, then you have one problem. Inside Kubernetes, there is a scheduler which is responsible for the allocation of the different applications on the worker nodes. And the typical Kubernetes scheduler is only allocation-based, so he doesn't consider power consumption. It's not interesting for him. And so we have decided to design an own Kubernetes scheduler, an own custom scheduler, and our own scheduler now considers nodes with higher energy efficiency, and he need a model, and we model the power consumption of the different devices. We use a regression line, and you see on all the slides before the equation of the different regression lines. And an example here for this Cortex A53, we have a regression line with a parameter A 0.0 to and 7.0928. So this is the base for the orchestration. And our scheduler uses only nodes, or tries to use nodes with smallest power consumption. And he's responsible for the installation. If you import a new application in your system, then he is responsible for the installation. And if there is something change in the configuration, to reorchestrate the application. So if there's a trigger coming from outside, there can be the need to move one application to another to reach a better power consumption of the system overall. Okay, now here a short overview about the protocol stack. We have on the hardware side, we have a control plane. On the control plane, there's running Kubernetes, a small version, a resource-efficient version of Kubernetes. And then we have different worker nodes. And one of these worker nodes can be, an example, an edge server. This is for the 5G radio access network. The edge server is a typical Intel server, a typical i7 Intel processor, and the radio units in our configuration that are typical the Xilinx FPGA boards I have shown before. Okay, our control plane is running Kubernetes, but the version K3S. This is a resource-optimized version, and this is responsible for the orchestration. Over the hardware plane, we have the runtime for the container. This is the runtime which is running on the worker nodes, and we have the Kubernetes framework. And over this, we have the scheduler plugin, our custom scheduler, and the energy manager, which is responsible for the orchestration process. Okay, here this slide shows step-by-step activation or doing of the orchestration. So typically we use an external actor. This can be a KI agent or a neuromorph system. We have our control plane on a Raspberry Pi. We have a worker node with a big performance based on an Intel i7 processor, and we have the different radio units with embedded systems, with an ARM processor, with a Xilinx FPGAs. And if the KI agent sees that there is a necessity of doing reorchestration, then it sends a message to our energy manager. The energy manager talks with the scheduler, and the scheduler now is responsible for moving, at example, an application. So if we have running an application on the i7 server, then the first task is to start the same application on the radio unit, then to do a movement of the internal state of the data, at example, from the application on the Intel server to the worker node, and then to stop the application. And this is the process of moving one application from one node to the other node. So Another interesting orchestration we have analyzed is that if you use FPGAs, so programmable hardware parts on your system, then you have the possibility to realize your functionality as a software component or as a hardware component. And if you have FPGA resources or hardware resources not completely realized, you have free FPGA resources, then you have the possibility to implement a software function also as a hardware function. An example in a manner of a coprocessor. Typical example is a neural network. So a neural network you can realize in form of hardware. So I show here this is a hardware adder and we have different inputs with different weighted. We multiplicate the input data and then accumulate all together. And if you use many of these resources, then you can build in a hardware a neural network, at example. Or you realize it as a simple Python program, and then you can run it on the processor. And the functionality of hardware virtualization means that if you have all into a container and you move a container, at example, to one worker node, then our framework analyzes, are there free resources in the FPGA, and if this is the case, then the hardware part will be loaded into the FPGA because the Xilinx FPGAs are partly reconfigurable, so you can, at every time you can load a new hardware functionality inside this FPGA. And if you need a hardware or you realize a hardware solution, then you also need a software because you have an interface between the hardware and the software. So if you have load a coprocessor into the FPGA, you need an interface software which is responsible for the communication between the software part on the ARM processor and the FPGA part where you have realized your hardware. And for us, it was interesting to see it is possible to save energy if you implement a special function, at example, a neural network, inside the FPGA resources, inside hardware or realized as hardware resources, or running as a software component. And here I show you some configurations. So on the left side, the first part, this is a neural network, 64 neurons with 1024 inputs, completely realized in form of software, of C code. So we use the programming language C. And you see on the blue side the calculation time. This is the speed of your implementation, which is always interesting. And on the green side or on the red side, you see different views of the consuming energy. And you see in C code, you have a long calculation time, and you have also a big amount of dynamic energy. And the next part of the diagram shows the same functionality, but complete realized inside the hardware of the FPGA, and you see the difference. But the problem is here, this is only the implementation. We have also in this implementation the need to make the interface communication between the software part and the hardware part, and this is not included in this diagram. And the next part shows an optimized code. So ARM has a special optimized, very near to assembler code. And you see that it's also possible to optimize the C code to get a better energy consumption and a better speed behavior. And then on the both diagrams on the right side shows one different methods to communicate between software and hardware. The right, which is really worst case scenario, this uses web services, so-called. They are using TCP/IP stacks and so on, and you see that it's very time-consuming and also very energy-consuming. The fourth solution here, FPGA via named pipes, used a specialty communication manner of Linux, and you see that this results in a very good performance and also in a very small energy consumptions in direct comparison to the optimized C code. So if you have free resources inside SoC with FPGA, it makes absolutely sense to realize a co-function, a co-processor inside the hardware function to get energy savings. Okay, this is only our hardware system we used to simulate or to modeling the all and to measure this. And now I come really to the workshop theme, so the things we want to realize during the next days. And in this case, we don't go into 5G radio access network. We have decided to analyze more an automotive use case. We also have analyzed in the project Green ICT, which is the base of the student camp. And in this use case, there we have a assistance system together with different radar sensors inside a car. And we focus especially on the signal processing of this radar sensor. The radar sensor system is coming from another Fraunhofer Institute, from the FHR, and they are working on the theme signal processing, energy efficient signal processing for radar technology. And here on the lower part of the slide, you show the system with a radar sensor. It looks a little bit like an egg, and different components of the signal processing. And we will analyze this use case in such a manner that we will have a look on the system on a functionality of a car without energy savings, and then we will show it is possible to find a part load situation, and it's really possible because if you are in different driving conditions, at example, if you drive into a town on a highway, then you have different speeds, and in these speeds, different speeds, you have the possibility to decrease the performance of the sensor systems. Because if you're on a highway, you have a high speed, then you have the need to have a very fast data acquisition. You need much data, and if you are driving, at example, in the town, then you can see the timings and the data resolution a little bit more relaxed. Okay, and then I come to my last slide. The picture on the right side is not so interesting. What will you learn during the next days? So now you have a little bit more information about energy savings in distributed embedded systems. And now for us, it is interesting that you analyze typical use cases where we can use such distributed embedded systems. So two we have learned today and yesterday. One was 5G communication, at example, and automotive is also one. But there are many, many different other use cases. And I think to use this technology, it's very important to find typical use cases where distributed embedded systems are used. Then for the complete energy savings with orchestration and virtualization, we have realized an own simulator which is based on Excel. And you will use this Excel simulator to analyze different distribution scenarios to optimize the system, to show which components you need on the system, and so on. And then at the last 2 days, we will make the calculation of parts of a life cycle assessment for the radar sensor use cases. So very important for energy savings with, in a distributed embedded systems is that you realize, is there a load curve? Is there a partly load? Or is there no part load? So you need always the complete full power of a system, the full performance. Then the mechanism we show here, you cannot use. So it's really important, is inside the car, or if you use a car, is there the possibility of a load curve? And then you will make comparison between the energy consumption of the systems with energy savings or without energy savings. At the end, you will calculate the possible energy savings over the next years, and you will analyze the carbon footprint of the use case. An example for the electric car, or the typical car today driving on the street. Yes, and at the end, perhaps we will have a discussion, makes this sense or makes this not sense? It's only, this use case is actually complete a theoretical use case. So it can be that it makes no sense. Now I can say, in comparison to the driving part, the motor of the car, it makes no sense. But this is not the target of this workshop. The target of this workshop is that we find a solution for the radar sensor, for the assistance system, that should be as energy efficient as possible. So, thank you.